Good day and welcome to Calculus 1. This will be part 1 of our discussion on tangents and velocities. And note, for all of these discussions, you can go to the associated course materials module in Canvas and find a blank note sheet to help you follow along. Now, today we're going to start off with a motivating question that will lead us very nicely into our next topic, which is limits, but we will also pick up again later on when we talk about something called differentiation. And our motivating example is a very simple question. Can we find the equation of the tangent line to the curve y equals square root x at x equals 1? And I'll note there's nothing special about the function or the point that we've picked, except for the fact that it's nice and easy for us to draw. So let's see if we can visualize this scenario. So the graph of the curve y equals square root of x is something that we should all be able to visualize. Roughly speaking, it starts at the origin and looks something like this. And what we would like to do is find the tangent line to the curve at x equals 1. So at x equals 1, the function output is going to be 1. So we have this point on the curve 1, 1. But what in the world do we mean by the tangent line? Well, the tangent line itself is kind of a vague term and maybe a bit difficult for us to give a precise definition to, but we could easily give some intuition. In terms of a circle, it's very easy to define what the tangent line is going to be. If you pick a point on the circle, the tangent line would be the line that only intersects the circle at that specific point. And then we can extend that idea just intuitively if we imagine having a portion of a curve, say y equals f of x, and we're looking specifically at a given point on the curve. The tangent line will be the line that only touches the curve at that point when you are close to that point. And intuitively what it is doing is giving the direction of the curve. If you imagine, traveling along a road, at this specific point, it's giving the direction which you are traveling. Now, in general, if we want to find the equation of a line, recall that requires us to find two different things. What we need is a point, and we need a slope. Now, for the curve in question, y equals square root of x, we most definitely already have that point, 1, 1. What we need to find is the slope of the tangent line. Let me go ahead and draw that tangent line in there. So roughly speaking, we have a line that looks something like this. And if we could find this slope, that's the quantity we need to find, then we would immediately have the equation of the line. The point slope form of the line would be y minus 1, where 1 is the y coordinate of the line, of the point, equals m times x minus 1, where once again the 1 is the x coordinate of the point. So this all hinges upon the fact that we need to be able to find the slope of this tangent line. Now, note, when you are finding the slope of a line, think rise over run, that typically requires us to know 2 points on the line. But the problem is we do not have 2 points on the line, we just have 1. So let me redraw the scenario of interest. We have the curve y equals square root x, and we have this point of interest 1, 1, and what we would like to know is the slope of the tangent line at that point. Now, even though we can't directly compute this slope in one step, what we can do is hopefully maybe approximate it as closely as we would like. So if we were to pick another point on this curve, let's go ahead and call this point q, and we'll think that it corresponds to some input x. So this would be the point x comma square root x, and we'll call this original point 1, 1, p. If I was to draw the line going through those 2 points, so roughly speaking, something like this, we would call this a secant line. A secant line is a line that passes through multiple points on the curve, and the slope of the secant line is something that we can easily compute. And I will call this m sub pq, with the PQ referring to the fact that it's a line going through P and Q. And we see specifically the points associated with P and Q. So the slope of that secant line is going to be given by the difference in their y values, rise, divided by the difference in their x values, run. And the observation that we want to make is this MPQ is not going to be the desired slope. But as the Q point approaches P, the slope of the secant line, M sub PQ, will approximate the slope of the tangent line. And this tells us exactly what we need to do. In order to find the slope of this red tangent line, what we need to do is let our input x for that point Q approach 1. And as it does, this secant line going through the points P and Q will in a sense kind of rotate around and begin to approximate that tangent line very closely. For example, let me just draw in a few of those secant lines. If we move x a bit closer and we draw the secant line through those 2 points, P and this new Q, versus if we go even a little bit closer yet, we see that those secant lines become closer and closer to approximating that red tangent line. And hopefully I haven't complicated the picture too much, but just giving you a bit of intuition behind how this is working visually. So now that we see what needs to be done, we need to collect a little bit of anecdotal data. That is, we need to think about for some x values close to 1, it could be on the right or the left, what is this slope MPQ going to be becoming close to? So we're going to make a table of some values. So first, thinking about from the right-hand side, for an x value close to 1, what is that associated slope of the secant line? And so some values close to 1 on the right, starting a little further away, maybe 2, 1.5, 1.1, 1.001. So getting closer and closer to 1. And note, these are very straightforward computations. We have a formula for MPQ above. So for example, when x is equal to 2, MPQ is the square root 2 minus 1 over 2 minus 1, where we're using this above formula. And if you just simply plug this into a calculator, this would be 0.4142. So when x is equal to 2, the slope of the associated secant line is 0.4142. If you were to do the same computation when x is 1.5, you would get back 0.4494. When x is 1.1, you get back 0.4881. And when x is 1.001, you get back 0.4998. And recall the key idea. As x is getting closer to 1, the slopes of those associated secant lines should be coming closer and closer to the value that we are trying to approximate, the slope of the tangent line. And note, these numbers are getting closer to what? 1/2. And our guess then is that m, the slope of the tangent line, should be approximately 1/2. But note we mentioned we can approach 1 from the right or the left, so we really have to double check and make sure that nothing different is going to be happening on that left-hand side. So we're going to make a similar table of values. We want to approach 1 from the left. So for example, we might start as far away as 0, then go to 0.5, 0.9, 0.999. And if we calculate the slopes of those associated secant lines, we would get 1.58579. And then at 0.9 for x, we'd get 0.5132. And then 0.50013. And once again, we see that as x is getting closer to 1, this time on the left, those secant line slopes are approaching 1/2. So putting this together, I'm going to make just a few observations. So the first observation that I want to make is that what we have observed through our anecdotal evidence. Note, we haven't proven or shown anything is conclusively true, but we have some nice supporting evidence. As x approaches 1, which it could do from the left or the right, the slope of that associated secant line, MPQ, approaches 1/2. And if we put this in terms of the notation that we are going to be seeing in our next section, we would say the limit as x approaches 1 of the slope of the secant lines MPQ is equal to 1/2. So at this point, we don't know with 100% certainty what the slope of that tangent line is going to be. But what we have seen is our above work suggests that the slope of the tangent line is 1/2. So putting this together with our initial observation, we now have that the desired tangent line, and note, to say that this suggests the slope of the tangent line is 1/2 is to indicate that we don't know this is true with 100% certainty. We haven't conclusively proven that this is true, but we've collected enough anecdotal evidence for now to suggest it is the case. Later on this semester, we'll have maybe a more rigorous method that we can use. And the tangent line at x equals 1 is given as y minus 1 is equal to 1/2 times x minus 1. And I am perfectly happy with you leaving it in this point slope form. If you would like to take it a step further, there certainly is no issue with rewriting this as y equals 1/2 x plus 1/2. And this completes part 1 of our discussion on tangents and velocities. In our upcoming video, we will discuss another seemingly unrelated problem, but finish by connecting it back to this idea of a tangent line. So stay tuned and take care.